Okay, so today we're going to be talking about the mean value theorem and Rolle's theorem. And Rolle's theorem is just a special case of the mean value theorem, so they're kind of the same thing. So what the mean value theorem guarantees is that for any function that is continuous and differentiable on an interval from a to b, there exists a point at x equals c between a and b, where f prime of c equals f of b minus f of a over b minus a. So let's draw this out and see what it means. So we have any function, right? We'll sum like this, cos f of x, right? This is a, this is b. And what you may notice about this equation here is that this is actually the slope, like the slope equation. Like it has the y2 minus y1 over x2 minus x1. So we can say that this line here, this like the slope of the line between these 2 points, right? There's just some point where the derivative equals the slope of that. So what this means is that we can move this line over to some point where it is tangent, right? Because that's what the derivative means. It means the tangent, right? It means the slope of the line tangent, right? So wherever this point, this line is tangent, that is our c. That's our c value right here. So thus all this theorem guarantees is that for some value of x between the two endpoints, the derivative is equal to the average rate of change along the interval. All right, and Rolle's theorem states, Rolle's theorem it's just a special case of the mean value theorem where f of a equals f of b. All right, and that guarantees that for some point on the interval, there's a value where the derivative equals 0. And we can get that by plugging these points into here anyways, since we'll get f of b minus f of a will be equal to 0. And to visualize this, on our interval from a to b, if the function values are the same, like here and here, no matter what happens like to the function, there's always going to be some point where the derivative equals 0, which would be right here on this one, right? Because that would be the average rate of change of this function on this interval. You can always slide it to somewhere where it's tangent. That's all the mean value theorem states. And Rolle's theorem is just a special case where the two endpoints are the same, so that means the derivative equals 0 at some point. So let's go through a couple examples. Okay, so given f of x equals 3 minus 5 over x on the interval 1 to 5, right? We are asked to first graph this and state that how the mean value theorem applies, and we have to find where that c is, where the derivative is equal to the average rate of change of this function. So first let's graph it, right? And it's going to look something like this, kind of like that. That's our f of x. And we're looking at from x equals 1, which is right around here, to x equals 5, which is up here. Right, so if we take this point here, which we can plug in, so f of 1 would be 3 minus 5, right? So that'll be negative 2 down here. So this point is 1, negative 2. in this point here, if we plug 5 in, we get 3 minus 1, so that would be 2 here. So this point is 5, 2. We can plug this information, these 2 points, into our mean value theorem formula and show that there's going to be some c where f prime of c is equal to, remember, f of b minus f of a. So 5 would be our b, and f of b is 2. So that would be 2 minus the function value of a, which is negative 2, over b minus a, which is 5 minus 1. So that's going to give us 4 over 4, or 1. So what this 1 tells us is that there's some point between 1 and 5 where the derivative equals 1, right? Where the slope of the line tangent to this graph is equal to 1. So the way we do this is we just set the derivative equal to 1 and solve for x. Well, to do that, we have to find the derivative. So f of x equals 3 minus 5 over x. And to make this easier to use the power rule, I'll write 3 minus 5x to the negative 1. As you know, negative exponents take the reciprocal of it. So take the derivative of this, prime of x. The derivative of 3 is 0, so we're just left with negative 5 times negative 1, which is 5. Since we bring down this negative 1, multiply by the negative 5, that gives us 5. And then x, and then subtract 1 from here. This is negative 2, which is equal to 5 over x squared. So this is the equation for the derivative, is 5 over x squared. So now what we do with this is we set it equal to this 1, since we know that somewhere on this interval the derivative is equal to 1. Right? So we get 5 over x squared equals 1. And from here we can just solve for x, right? So we can go x squared equals 5 by multiplying x by both sides, and take the square root, we get x equals plus or minus square root of 5. And now, since we have to decide between plus or minus, we have to look at which one is in the interval, since we know c has to be between a and b. So that rules out negative root 5, because that'll be outside of this range. We know that x equals square root of 5, and that's our answer. And so what this square root of 5 means is that at root 5, which is like a little past 2, at like root 5, the derivative at this point is equal to 1, and that's equal to the average rate of change of this function. We can see this by drawing a line between here, and if we slid this line up to where it meets the square root of 5, it would be tangent to this graph, right? And that's how we use the mean value theorem for that. And we'll do an example of Rolle's theorem, right? So for this one, we are given f of x equals x squared minus x minus 6 on the interval 2 to 3, negative 2 to 3. And here we have to show that Rolle's theorem applies, and then find where the derivative equals 0, right? Okay, so here to show that Rolle's theorem applies, we just have to show that the function value at these 2 points are the same. So if you remember, if the function values at the endpoints are the same, that's Rolle's theorem, because it guarantees that somewhere on that interval the derivative equals 0. Okay, so to do that, we have to plug in the endpoints and see if they're the same. So f of negative 2, we get negative 2 squared minus negative 2 minus 6. That gives us 4 plus 2 minus 6 equals 0. All right, and if we plug in 3, we get 3 squared minus 3 minus 6. That'll be 9 minus 3 minus 6 is also 0. So this shows that Rolle's theorem applies because these two values are the same. And notice that these two don't have to be 0. Like this could be 3 and this could be 3. It doesn't have to be 0 because the average rate of change on that on that interval or that function will be 0 if they are the same. So Rolle theorem applies to this because this and this are the same. The function values at these 2 points are the same. So now we have to see where the derivative equals 0 on here. So to do that, we have to take the derivative, right? So we have x squared minus x minus 6. And to take the derivative, use the power rule to get 2x minus 1. And so here, we just have to set it equal to 0 because the Rolle's theorem says that between two endpoints, if they are the same, the function values at the endpoints, if they are the same, somewhere on the interval, the derivative equals 0. So from here, you just have to set this equal to 0. All right. So 2x equals 1, and x equals 1/2. And you are done. And again, what this 1/2 means is that at f of x equals 1/2, this function, like the derivative of this function at 1/2 is equal to 0. And that's also equal to the average rate of change of that function over this interval, because that's what the mean value theorem states. And yeah, that's an example of Rolle's theorem. All you need to do is check the endpoints for Rolle's theorem, check the endpoints. If they're the same, that says that the derivative equals 0 on that interval somewhere. And if these are not the same, then mean value theorem applies. And it just says that somewhere on the interval, the derivative equals the average rate of change, which is the f of b minus f of a over b minus a, because that's the slope formula. All right, so that is the mean value theorem and Rolle's theorem, and yeah, that's it.